Hello and welcome to our video on the hydrogen fuel cell. Today we'll be going over a couple of things. So firstly, how do we actually get the hydrogen that we're going to use in the fuel cell? Secondly, we're going to be going over two fuel cells that you need to know for year 12, one with an acidic electrolyte and one with an alkaline electrolyte. Next, we'll have two comparison tables, one going over the advantages and the disadvantages of the fuel cell itself, and secondly, another table going over the fuel cell when compared to the galvanic cells that you covered on your modules on electrochemical cells. So before we go into how we actually get the fuel for the hydrogen fuel cell or how the hydrogen fuel cell actually works, it's important you understand what it looks like in everyday life. So the main concept of the hydrogen fuel cell is that we use hydrogen as the fuel and we convert the chemical energy in the hydrogen into electrical energy that we can use either in a car or to power our homes. The main applications that have been instituted are in cars, especially because we don't have the power to power homes just yet, but especially in cars we're able to get hydrogen as the fuel to power cars such as like the Toyota Mirai, which goes into production soon. Essentially, we have a short schema on the left hand side that goes through this example. So instead of petrol for a normal combustion engine car, you can think of the petrol being substituted with hydrogen for a hydrogen fuel cell car, where we would store the hydrogen in a tank like this. Essentially, we then pump hydrogen into the fuel cell here. This fuel cell serves the purpose of, like I said, converting the chemical energy present in the hydrogen into electrical energy, which is then stored in a battery. These batteries are then able to power motors and eventually drive the car forwards. The advantages of this is it's relatively clean, it's carbon neutral, and the waste product is water vapor, and you don't get any toxic or noxious gases coming out of the car. So now that you've got a fairly good understanding of what the hydrogen fuel cell is, we'll start our conversation by talking about where do we actually get hydrogen in the first place. So currently there's two main ways in which we can retrieve hydrogen. Firstly, there's the steam reforming process, in which most of the world's hydrogen is produced. However, the disadvantages of this process is that it's not particularly green or carbon neutral. The second process that we're going to go over in the next slide is a lot more green and carbon neutral. However, we'll start with the steam reforming process first. With the steam reforming process, we're converting natural gas or methane in natural gas, I'll grab my pen, methane in natural gas into hydrogen. What that looks like, or how we do that, is by reacting that methane with high temperature, 800 degrees Celsius, and high pressure, 20 to 30 atmospheres, steam. That's H2O liquid. That gives us carbon monoxide and hydrogen. It should also just be stated, these two slides you don't particularly need to know for your Year 12 chemistry syllabus. I've just put them in as some extra context. For this reaction, you use a nickel catalyst. And this is an endothermic process. This carbon monoxide then reacts with the same high temperature, high pressure steam to give you carbon dioxide and more hydrogen. So basically, from that methane and water, you've produced a grand total of 4 hydrogens in total from the original methane and water, not just the methane. Overall, this is an endothermic process, so the laws of Le Chatelier's principle and increasing reaction rate due to increasing temperatures both apply. So thus, by having that high temperature and high pressure steam, we can eventually create an increase in both yield and reaction rate. So the second way we can retrieve hydrogen for use in the hydrogen fuel cell is by the electrolysis of water. Now you may have covered this in schools or on a video on electrochemical cells, however we will go through this reaction quickly in the way of review. Essentially down the bottom is the overall reaction that I have here. I'll change colors to show that. So basically we're breaking down water into hydrogen and an oxygen gas molecule. Essentially, we're using an electrochemical cell to do this, or an electrolytic cell to do this. And the way in which we can make it clean is by, instead of using this battery, we don't use a battery, we use solar energy or any use of green energy that we can find. We have an oxidation reaction that's happening at the anode, and this is what I like to do, thinking of these systematically. So you have 2 molecules of water that are being oxidized to give you oxygen, a high hydrogen ion, and 4 electrons. At the cathode, these hydrogen ions are then accepting 2 more electrons from the 4 that are produced from hydrogen gas. So thus overall, water is forming oxygen and hydrogen gas if you balance these out. So with the storage of hydrogen, there are two main considerations that we need to think of. Firstly, the fact that it's incredibly flammable, so we need to store it safely. And secondly, the fact that it's a gas, and that presents challenges on its own. There are two ways in which we can store it. Firstly, one's kind of intuitive. If gaseous substances are hard to store, we can make it a liquid, and we can do this by cooling it at minus 252.8 degrees Celsius, or we can store it as a compressed gas at incredibly high pressures at 350 to 700 atmospheres. The reason why I bring this up is to show you that the storage of hydrogen is a big challenge. It's not as easy as storing a fuel like petrol, for example. So in year 12, you'll need to know about two main fuel cells or hydrogen fuel cells. The main way in which they differ is one has an acidic electrolyte, and we'll go over the basic structure of both of the cells in the next couple of slides, and one is going to have an alkaline electrolyte. We'll begin our discussion on those with an acidic electrolyte. There are four key points that you need to know. Firstly, the electrolyte is, although acidic, in specific it's usually phosphoric acid. They have a lower efficiency compared to the compared to fuel cells with alkaline electrolytes, and they operate about 40 to 80% efficiency. They have a much higher operating temperature of about 150 to 200 degrees Celsius, and they have a good power output of about 200 kilowatts. So we'll start by going over some of the components of the hydrogen fuel cell with the acid electrolyte. So on the left-hand side, you have hydrogen gas entering the actual fuel cell. You have an anode and a cathode, both coated with a platinum catalyst, so I'll say PT catalyst. You have an electrolyte, which is aqueous phosphoric acid, so I'll write H3PO4. In this reaction, what you're making is you're making water, which is exiting, and you have air that's entering the cathode side. The whole fuel cell is attached to an external circuit, and recall that electricity is the flow of electrons. So with the fuel cell, if we generate electrons and get these electrons to move through a circuit, we've effectively made electricity, which is our goal for these hydrogen fuel cells. So how do we actually make electricity in this hydrogen fuel cell? So on the left-hand side, we have hydrogen entering, and on the right-hand side, we have oxygen entering. All this hydrogen and this oxygen want to do is react and form water and leave the fuel cell. However, we have an obstructive barrier, which is the electrolyte, that's preventing the hydrogen from going from the left-hand side to the right-hand side. So it can't do that in the presence of the electrolyte. Now, although hydrogen can't, what can go through the electrolyte is H+ ions. So hydrogen kind of morphs into the H+ ions at the anode, and that is what we call the oxidation reaction. So hydrogen is oxidized to form two H+ plus two electrons. Now we have H+ approaching the cathode end and trying to react with the oxygen. However, H+, which is hydrogen without its outer shell electron, can't really effectively react with elemental oxygen. However, hydrogen gas can. So what happens is H+ will accept an electron or two electrons and reduce oxygen to form H. So effectively where we left off was hydrogen oxidizing at the anode to form two H+ ions and two electrons. Now, at the cathode end, those two H+ ions, if you like, will diffuse across and meet oxygen at the cathode end. However, H+ can't really react with elemental oxygen. However, hydrogen, or hydrogen gas, it definitely can. What H+ needs to do is go back to hydrogen, and effectively it does this by accepting two electrons. However, we've already made two electrons when H2 gas was oxidized to form two H+ and two electrons. That's these two electrons here. These two electrons will travel across this circuit and onto the other side and combine with the H+ that we made, and a reduction reaction will happen at the cathode, where oxygen will react with H+ and the two electrons we made from the oxidation stage in the anode to give you water. which we can excrete. And this is the overall reaction. Hydrogen gas and oxygen gas combining to form water with an electric potential of 1.35. Also recall, with these electrolytic cells, the electric potential of the cell is the electric potential of the cathode minus the electric potential of the anode, which is 1.23 minus 0, which is 1.23. So thus, for this hydrogen fuel cell with the acidic electrolyte, we get an overall potential of 1.23 volts, and you can find both of these on your data sheet. So for the alkaline cell, we have a couple of similar conditions that we need to go over. So firstly, the fact that we have the electrolyte, which is an alkaline electrolyte in this case, and that tends to be potassium hydroxide. We have an efficiency that's a little bit higher when compared to the acidic electrolyte hydrogen fuel cell of about 60 to 80%. We have an operating temperature much lower at 90 degrees Celsius when compared to the other cell, and we produce about the same power. So as you can see, we do prefer using the alkaline electrolyte hydrogen fuel cells over the acidic electrolyte hydrogen fuel cells. So we'll start going over the cell now. So again, we have the anode and the cathode both lined by a platinum catalyst. Unlike the hydrogen fuel cell with the acidic electrolyte, we have hydrogen coming in the one end, but also water leaving in the same end. And recall that in the acidic electrolyte hydrogen fuel cell, water would come out on the other end, and that's significant, and you'll see in a bit why. We have air or oxygen entering this end, and we have an external circuit that binds the anode and the cathode and facilitates the transfer of electrons, which we said is electricity. So we'll go over the cell now. So essentially what happens is we have hydrogen coming in through this inlet here. At the anode, we have an oxidation reaction happening where hydrogen reacts with the hydroxide ions present in the potassium hydroxide electrolytes. So the hydroxide ions reacts with this hydrogen, and essentially it undergoes an oxidation reaction where we have 2 molecules of water and 2 electrons produced. So essentially that creates 2 molecules of water and 2 electrons. So at the next step, we've produced these 2 molecules of water and we've got 2 electrons. These electrons, if I grab my pen and redraw those 2 electrons, these electrons are free to travel in the external circuits, and I'll get rid of them here. And this water meets those 2 electrons, and at the cathode, we have an oxidation reaction happening with all those things. So oxygen, water that we produce from the oxidation step at the anode, and the 2 electrons that we've also produced here. So essentially these 2 things react to form your original hydroxide. So you get OH being reproduced. So essentially the overall reaction is pretty much the exact same. We have hydrogen and oxygen combining to form water. Very similar in both cells. We're producing electrons and they're forming at the anode, and then they travel through the external circuit and meet at the cathode, and they produce another reaction. So that's how both of these cells produce electricity. They just tend to do it in different manners with different electrolytes. With regards to the overall potential, so if we draw the formula, so if I grab my pen, so that's the formula for the overall potential. You can grab the potentials for the half reactants from your data sheet, and if you plug it into the formula, you get 0.40 minus 0.83, which is 1.23 volts, which is exactly the same as the electric potential of the acidic electrolyte hydrogen fuel cell. So thus, it's important to understand that both cells produce the same potential. They just do it in different ways. So they have different electrolytes and they have different reactions at the anode and the cathode as well. And what process is happening at the anode and at the cathode is different for both of the cells. So there are some important considerations for the hydrogen fuel cell. Firstly, the anode and cathode that we're talking about are porous in nature. So they're not big blocks of metal. They have fine little pores in them that allow the gases to freely float through or diffuse across. Also, these anodes and cathodes are lined by catalysts such as platinum, which helps the reaction proceed. The alkaline fuel cell is very sensitive to carbon dioxide gas because the potassium hydroxide electrolyte can react with the carbon dioxide to give you potassium carbonate, and we don't want that because that decreases the overall amount of hydroxide, which, as you may have recalled, is a key part of that reaction. If we have a decrease in hydroxide because of the carbon dioxide gas, we get a result of a decrease in performance, and we don't want that. One other thing to take in mind is that these fuel cells, we can actually connect them together in series. So we can have lots of these fuel cells stacked up one on top of another, connect them all together, and we get one large fuel cell effectively working together, and we get an increase in power output. So that's a way we can maximize power output. One problem with that is if we have that one large fuel cell, we produce water. So if you go back to the original reaction, hydrogen and oxygen are effectively producing water. Over time, what will happen is this water will build up and decrease the concentration of something as key as the electrolyte. So if the electrolyte goes down in concentration, it won't be as effective of doing its job, such as oxidizing, for example. And if it can't do its job, the overall performance of the cell goes down. So now we'll go over some distinct advantages and disadvantages of using a hydrogen fuel cell as a source of energy. So we'll start with the advantages. The fuel cell converts chemical energy directly into electrical energy. So that's a one-step process. You have the hydrogen, you inject it into the fuel cell does its magic effectively, and you get electrical energy produced. With a process such as coal, it's a multi-step process where you have energy leaks in the way. So overall, the hydrogen fuel cell is, number one, more efficient, and number two, a lot more greener and cleaner than coal-powered energy. Also, fuel cells can generate electricity as long as we supply them. So especially with cars, for example, we can have an electric car, but that's something that needs to be recharged. Whereas for a hydrogen fuel cell, we can constantly make electricity provided that we have hydrogen on board. So there's no sense of range anxiety, if that makes sense. Some disadvantages is, on that note, we do need a constant supply of fuel. So we do need hydrogen to be stored and emitted into the hydrogen fuel cell itself. On that note as well, as an extension, the infrastructure for hydrogen fuel cells just isn't there yet. There are a couple of fuel stations for hydrogens in Australia, but definitely not anything as like a statewide or nationwide rollout just yet. They're incredibly expensive. They operate at high temperatures. One of the main costs is platinum. So the catalyst that lines the cathode and the anode is made out of platinum, which is incredibly expensive. And last but not least, they generate a direct current. We need a converter to convert that into AC current, which is typically what your household voltages use. So the main way a galvanic cell will differ from a fuel cell is that in the galvanic cell, the reactants are actually part of the anode and the cathode, so they degrade over time. However, with the fuel cell, we actually provide the reactant, so we're providing the hydrogen, we're providing the oxygen, and so on and so forth. On that note, the galvanic cell tends to be a little more efficient. However, the fuel cell is still rather efficient, and due to the fact that we don't need to really replace any of the anode and the cathode too regularly because they're not used up, we can just supply the fuel. That makes that, albeit small, decrease in efficiency rather good in the long run.